Hi, everyone, and thanks so much for joining us today. We're going to kick things off and get started here. My name is Teresa, and I will be moderating today's one-hour webinar. I would like to formally welcome you to today's event, Updated Guidelines for the Design of Fender Systems, presented by PIANC USA. Before we get started, I'll take a quick moment to review the webinar platform that we'll be using. From the toolbar at the bottom of your screen, you can mute and unmute your line. You can also raise and lower your hand and interact non-verbally via reactions. Use the chat panel to send questions or comments, and we will have a brief question and answer session at the end of the webinar. All participants are eligible to earn 1 professional development hour for attending today's event. A password is required to retrieve your customized PDH certificate, and we'll provide that password at the end of the webinar. If you have to duck out early, don't worry. A recording of today's event will be emailed to you and will be posted on PIANC USA's YouTube channel. Finally, our presenter today will be Rune Iversen. Mr. Iversen has over 20 years of experience in the marine industry. After working as a naval architect for 6 years, his experience has been focused on inspection, condition assessment, rehabilitation, and design of mooring and berthing systems and marine structures. With that, I will hand off today's presentation to Rune Iversen.
All right, thank you very much. I think you should be able to see the screen here right now and hopefully hear me as well. So welcome. I'm going to give an introduction to the updated guidelines for Design of Fender Systems that have been prepared by PIANC Working Group 211. We're going to go through a few little things there. We're going to have an introduction to the working group members, specific topics for our document, research that has been done as part of the development of the document, the status of the working group right now, and also what the next steps are. Then we're going to get into discussing berthing velocities. I know many of you will be interested in hearing about that. Some of the background behind berthing velocities, why there's been efforts to collect a lot of new data that's been used for this document, the specific data collection that was done, the measurements, how we did the measurements, how the data was collected and recorded, analysis of the data, and then finally some results. And the third topic we're going to touch on today is the energy factor, formerly known as the abnormal berthing factor, that you use when you design Fender systems. Again, we're going to talk a little bit about the background behind this factor, challenges, working group 211 approach, safety classes that we have considered developing this energy factor, and the other contributing factors, and then finally the results of that work we did there. So let's do an introduction of the working group here that's been really put together a great effort developing this document here. On the left here, you can actually see Eric Brose, who is the chairman of the committee here. And I think he actually is attending this call today too. So the motivation for developing this document really comes from, it all starts with PIANC Working Group 33 that I think all of you know about. The guidelines for the Design of Fender Systems was published in 2002, and it's really been the key document, the big reference document that everybody's referred to throughout the world when either countries have developed their own standards for fender design, or if you just needed another reference to use if there isn't a specific guidance in the country where the design is taking place. Since 2002, there has been a lot of evolution in vessel dimensions. There's been a lot of new work done on collecting data on actual berthings, velocities, angles, how do things actually happen. We're dealing with new materials, new studies that have been done on durability aspects related to fender performance. There's also been discussions regarding specific fender testing and the verification process of this testing. So in 2018, PIANC MarCom requested to start a new working group, which was PIANC Working Group 211. And the main task is really to update this document from PIANC Working Group 33. The terms of reference for the working group can be summarized in these bullet points here. We wanted a document to be aligned with current practice in fender design, and also with current practice in other structural designs, such as reliability design methods and semi-probabilistic approach to ensuring a good level of safety in your design. We wanted to use the latest simulation software for evaluation of fenders and vessel interaction. We wanted to take into account recent trends in vessels, so evolutions in vessel geometry, vessel size, and hull shape. We wanted to take a close look at vertical and horizontal forces on fenders, allowable hull pressure, special issues applying to wheel fenders and foam film fenders. Also very important, take into account the output from PIANC Working Group 145 regarding berthing velocities, and then to verify all the relevant standards related to fender design, manufacturing, and testing. The members of the working group are listed right here. It's a total of 27 members from 12 countries here. As I mentioned earlier, Eric Rose from the Port of Rotterdam is the chair of the committee. We have had meetings several places around the world over the years. Started in the Netherlands, had a meeting in China, the UK, Australia, Spain, and also several online meetings. The last meeting we had was in October 2022 in Germany. And I think one of the real strengths of this working group here is the wide variety of members we have in the working group here. We have port authorities represented from Port of Rotterdam, Port of Bremerhaven. We have naval architects, we have consultants, contractors, marine contractors. We have representatives from OCDI. We have authors from the Japanese guidelines. We have all the major fender manufacturers in the world represented in the working group, and also research institutions from both Japan and the Netherlands. And also we have a master mariner as part of the group. So I think really this working group here, we have members that come from all sides, how it relates to fender design. Not only the people who design them, we have the people who use them, the people who actually construct them, but then also some people who are actually on a vessel and can see from that side how the fenders perform when vessels come in. So the content of the working group here is quickly summarized here. We're looking at just general aspects of fenders. This closely aligns with what was done for Working Group 33, but with a few additions. We're looking at an introduction to the principles of fendering, particular aspects regarding design vessels. It's actually some excellent work that's been done by one of our members to unify design vessel data across all PIANC documents. We're looking at the basis of design chapter. What parts do you need to consider when you're designing a fender system? Fender selection, fender system design. How do fenders respond to moored conditions? Manufacturing of fenders, important, and also how they're tested. Installation, inspection, and maintenance. Sustainability is actually a new thing that we have considered here, and we got some good information in that chapter as well. Specification writing, and then of course the references. And on the right, you can see a draft of a flow chart we have for how to properly design a fender system. This is still in the works, and we'll probably see some updates going forward. There's been a lot of research and development done as part of this working group. An important paper was, or important thesis that actually was done, was done by Felix Orlean at the Delft University, reliability-based assessment for Fender system. That work that he did is really the basis for a lot of the work you will see at the latest part of this presentation here. TNO in the Netherlands have done several studies on hull pressure. I already mentioned PIANC Working Group 145 on berthing velocities. We've done studies on allowable hull loading due to fender contact. There's actually two master's theses that have dealt with that subject. We have considered work from PIANC Working Group 167 for design of terminals for RoRo and RoPax vessels on hull pressure and belting. And then also in-house research from the fender manufacturers on fender materials, fender performance, fender durability, and impact of aging. I mentioned the thesis by Felix Orlean on reliability of fenders. It's really important work, and really when we came into this working group, we realized there wasn't much insight into the specific reliability of a fender system. So we took a probabilistic assessment to fender design, used statistical data that we had available on berthing velocities, and really tried to understand how does all this affect the reliability of the fender system. We're going to touch upon that a little bit more later in this presentation. As I mentioned, there were studies done on hull pressure, two master's theses that looked at this, and this was really driven by us realizing that typical tables for hull pressure that are published today, nobody could really tell us where all those numbers came from, and we could not figure out exactly what was the background, where did all the numbers for allowable hull pressure come from. So we did. There's been a fair amount of work performed on hull pressure to make sure that we understand these numbers properly. This shows a quick example on some numbers and some calculations that were done for ultra-large container vessels, 19,000 TEUs and above, and the published criteria is 200 kilonewtons per meter squared for these fenders. So 20 tons per square meter, roughly speaking. And the study here showed really that as fender panels get larger, the allowable hull pressure on the ships actually will go down. So there is a sweet spot there in terms of fender panel size. Larger panel isn't always better. So if we look at the status of the working group, the group started in March 2019. The report, I think now is 90% plus complete. The plan is to deliver a draft and hopefully a final report in 2023. Short title, PIANC Fender Guidelines 2023. There's a much longer title, official title of the document here. PIANC MarCom Working Group 211 Report Guidelines and Design, Manufacturing and Testing of Fender Systems 2023. Next steps for the working group is to nail down the final details on the subject you see here, vessel characteristics, mooring loads on fenders, allowable hull loading, we talked about that already, fender panel design, fender testing and durability, sustainability, recycling. And pay attention in the future. There will be more updates from the document given at conferences coming up. First one, PIANC USA in 2023. In Fort Lauderdale, I think that is in April next year. Possibly COPEDEC in 2023, which I think is in Manila, and then there's the PIANC World Congress in South Africa planned for 2024. So with that, we're done with the summary of the working group, and now we're going to start talking a little bit about berthing velocities and the results from PIANC Work Group 145 and where we've gone past that. So we're going to talk a little bit about just the introduction and the motivation again for looking at the berthing velocities. So from PIANC Work Group 33, which has been widely accepted in this industry, published some berthing velocity curves from a study by Brolsma in 1977. The curves were based on a limited number of measurements and a lot of extrapolation in the curves. And I think one of the real weaknesses, if you want to call it that, with those curves is that they show a really strong negative correlation when it comes to berthing velocity versus vessel size. So vessel sizes get bigger, berthing velocities go down, and that's not necessarily what happens once you get up to certain vessel sizes, you will see. I think everybody here hopefully knows what or seen this equation for calculation of kinetic energy of a vessel coming in that needs to be absorbed by a fender. And one of the important things here is that in 2010, in a study done by Professor Ueda from Japan, it was determined that the uncertainty in berthing velocity dominates the uncertainty in berthing energy, with about 85% contribution on that uncertainty from the velocity. So the velocity clearly is a very, very important factor to consider when you are designing fenders. And so a lot of work was done to collect data and analyze the data, figure out how can we improve on the data set that was published by Brolsma. There was a lot of data collected through PIANC Work Group 145. There were several methods used to collect this data. Interviews and questionnaires with vessels and marine terminals, use of laser docking aid systems, some who are permanently mounted on piers and wharves, also data from portable pilot units, high-resolution portable pilot units that are on the ships themselves. And then there's also portable smart dock workstations that can be used to measure the velocities of vessels coming in. At the bottom here, there's a table that summarizes the data that was collected through PIANC Work Group 145. We actually had data for almost 2,500 data points on berthing velocities and about 1,850 data points for vessels larger than 30,000 deadweight tons. And this is across for terminals across the world and also across several different categories. So bulk carriers, container carriers, LNG terminals, oil tank and oil tankers. One of the locations where velocities were recorded was at the Port of Rotterdam, where you have favorable berthing conditions. And I think there was actually 6 separate berths there that provided data to the study that was done in the PIANC Working Group 145. So 3 container berths that you can see in blue. Actually 7 terminals, so 3 container terminals, 3 tanker berths, and 1 bulker berth here. As part of collecting all this data, there was a lot of information collected along with just the velocity and the angle that was recorded. So general data for the terminal, what kind of site conditions do you have, name and type of terminal, what kind of waterfront structure are you dealing with, is it exposed or sheltered, berthing conditions, and also what type of fenders do they have at these sites. Vessel characteristics is important, so you know what size vessels you're getting velocities from. Actual physical conditions at the site. What wind did you have when the measurements were taken? How much waves was it? How much current was it? what tide level was it, so you can get an idea of the under-keel clearance for the vessels coming in. I mentioned the most important data points, the berthing velocity and the berthing angle. And then lots of other miscellaneous information was collected when possible. Were the ships assisted by pilots when they were berthing? Did they have tug assistance? What windage area did they have on the vessel? What type of cargo did they carry? What type of maneuver did they have coming in? Was it a parallel berthing or was it a more angular berthing? And so forth. So if we look at some of these data sets that were selected here, I'm going to give you a couple of examples of this. So this is one example from the Port of Rotterdam for container vessels. This is all really data from a sheltered condition with parallel landing of the vessel. Average berthing velocity is pretty low, 3 to 4 centimeters per second. So you're looking at 0.1 to 0.11 feet per second. Maximum berthing velocity of 10 centimeters per second. Low berthing angle. So this is about 3 months worth of data you're looking at here. But so if you're comparing this to the red curve at the bottom that was published in PIANC Working Group 33 for good berthing under sheltered conditions, with all this falls under, you see that all these data points are almost centered around that curve, especially for larger vessels. As you're going to see in a couple of slides, that's really not, that means that curve really isn't safe for to use for fender design at this facility here. We have another interesting data set from Bremerhaven, again, container vessels. This is actually an exposed site with high tidal currents, more angular landing of the vessels coming in. Average berthing velocity is 5 to 6 centimeters per second, with a maximum berthing velocity in the first set of measurements that were collected here of about 20 centimeters per second. But in 2018, there was actually a couple of measurements of about 26 centimeters per second. So if you translate this to the to conditions here in the United States, you're looking at 0.8 feet per second berthing velocity for vessels coming in here. Those were combined with very low berthing angles. And here you're actually looking at about 8 years of data from this terminal. So these records from this very large, almost largest container vessels in the world coming in really spurred some more research into how can we account for multiple fender contact when you're designing a fender system. And we're going to touch upon that later here. So I mentioned earlier how we don't want our data to be completely centered around these berthing velocity curves that we're going to use for fender design. And this all comes back to the studies that was done by Brolsma. If you read Working Group 33, it will say somewhere there that you're looking at average velocities. But this isn't average velocities as an average of all velocities that have been measured. The average velocity that's referred to in Working Group 33 is the average of the 1 in 3,000 return period velocities that you can see at the berth. So berthing velocities that are published are supposed to be a rare event. So this one, 1 in 3,000, you're assuming 100 berthings per year. You were actually looking at the return period of berthing velocities of about 30 years. So if you have a lot of berthing velocities around the curve that you're using, then it's difficult. But then you can't say that those velocities are safe to use, because you want to use that very rare event, the 1 in 3,000 event that now has been upgraded to a 50-year event, so 1 in 5,000 event. That's what you want to use for your design. So if we look at some of the data here, and now we're looking at, again, the 50-year return period that I referred to, there's two curves that I'm showing you here. So one for unfavorable conditions and one for moderate conditions. And I understand in PIANC Work Group 145, these were referred to as curve A and B. So we're looking at 1 in 5,000 berthing velocities, and the curves were developed for ships higher or larger than 30,000 deadweight tons. And we saw how this velocity actually develop as you go up in vessel size. This is how the curves actually compare to the measured data. So you can see your design velocity was much higher than almost all of the data points that you have recorded. If you're looking at the red dots below where the yellow dots here, and imagine where the average is of these based on the density of dots, you can see that the design velocities often are maybe between 2 and 3 times higher than the average of all the velocities that you have recorded. Now, if we take these curves and compare them to the design curves that were, or berthing velocity curves that were published in PIANC Working Group 33, you can see that these two curves show much higher velocities for vessels larger than 30,000 deadweight tons. And this really is something that's been consistent in all the data that has been collected so far. These velocities are higher than most all cases for these larger vessels than the curves that were published now dating back all the way to 1977. So how are we proposing berthing velocities in Working Group 211? Well, the real preferred situation and what the recommendation is to use local or site-specific information. That data is, if that is available, that data is always going to be better than the generalized berthing velocity curve that's been published by PIANC, no matter how well we collected that data. You can use berthing speed limits, if any, to using that local data. If you're doing a local study, you have your local data. The 1 in 5,000 event that I mentioned, so a velocity that has a probability of exceedance of 0.02%, that should be your design berthing velocity to be consistent with the curves that have been published by PIANC. If no information is available, there will be a table presented as part of Working Group 211 that can be used by designers. Velocities might be slightly conservative. This isn't all finalized yet either, but really here what you see is a range from about 10 centimeters per second, so 0.33 feet per second for the largest vessels under favorable conditions, and up to 30 centimeters per second under unfavorable conditions for the smallest vessels. And again, this is a concept. This isn't finally set in stone yet, but this is the velocities that are being proposed here. If you have velocity monitoring systems in place, then we will suggest that these velocities can be reduced by or reduced to as little as 80% of these velocities, because it actually turns out when you have these berthing velocity monitoring systems in place, berthings actually are a little bit more controlled. So I'm going to show you guys a couple of videos that show what some of this looks like. The first video is from the Port of Rotterdam under favorable navigation conditions. It's a container terminal, vessel sizes from 70 to 171,000 deadweight tons. Average velocity at this site, it's about 7 centimeters per second. There's a higher maximum recorded velocity. I see it says 7 here too. That must be a typo right there. But also generally very low berthing angles. As you can see, this is a very uneventful berthing happening at this site. We go to the next site. This is a site from Northern California. under moderate berthing conditions. It's a liquid bulk terminal. Vessel size is between 30 and 190,000 deadweight tons. Vessel coming in here is about 50,000 deadweight tons. Average velocity about 5 centimeters per second. Maximum measured about 15 centimeters per second for these vessel sizes. Again, typical berthing angles are between 0 and 2 degrees. Last one here is a little bit more dramatic. This is in the northeastern part of Europe under moderate navigation conditions. There's a breakwater protecting the site, but a pretty harsh wind climate. Container terminal, berthing velocities or measured berthing velocities between 10 and 15 centimeters per second. So you're talking between 0.33 and 0.5 feet per second here. But again, low berthing angles. But you will see that these fenders are actually doing their job and are getting worked pretty hard for this vessel coming in here. So if we go to the conclusions, our short conclusions here on berthing velocities, is that in general, the recorded berthing velocities are lower than recommended design velocities currently used in Fender design. But that's what you expect to see, since our design berthing velocities are a very low probability event. However, larger vessels, existing design codes really appear to underestimate the design berthing velocity. Maximum recorded berthing velocity was 10 centimeters per second, 20 centimeters per second, and 26 centimeters per second for favorable, moderate, and unfavorable navigation conditions. The data analysis really does not confirm a very strong negative correlation between the berthing velocity and vessel size. So really, once you get over a certain vessel size, berthing velocity does not change much. And if there's no recorded data or local information available, berthing velocities listed in the table I showed you here can be considered in the design of Fender systems. All right, so now we're going to go onto the last topic here, which is on the berthing energy factor or improvements on the abnormal berthing factor that's been used in Fender design for many years. Background for this, we talked about berthing velocity already, but we're gonna talk a little bit here about structural reliability and berthing safety factors, the challenges faced by the working group, the approach we took to the analysis, and the results from the analysis. We talked about where the old berthing velocities came from, what they actually represent, and in PIANC Working Group 33, it says about the abnormal berthing factor that it should be applied to enable reasonable abnormal impacts to be absorbed by the fendering system without damage. So you basically want an additional level of safety above your design berthing velocity, your design berthing scenario. Working Group 33 suggested a range of abnormal berthing factors for tankers and bulk cargo ships. It was suggested the smallest abnormal impact factor, or an abnormal impact factor of 1.25 for the largest vessels, 1.75 for the smallest ones. Container vessels, similar number, 1.5 for the largest vessels, 2 for the smallest ones, 1.75 for general cargo vessels, 2 for ro-ros and ferries, and 2 for tugboats, workboats, etc. But an important part of Working Group 33 is that it actually tells you to consider all these other factors too. So it says you should consider the effect of fender failure on berth operations. What happens if you lose a fender? Do you have to stop operations, or how do you deal with it? How often do vessels come in? I mentioned earlier, right, that berthing velocities are based on them now and are going to be based on a 1 in 5,000 event. What if we have vessels that come in much more often than 100 berthings per year, or much less often? You should consider this if you have berths with very low approach velocities that you use in your design. What is the vulnerability of the structure supporting the fender or the fender system? So for instance, a monopile dolphin might be a lot more vulnerable to an overload than a marginal wharf or a solid key wall. The range of vessels using the berth. So, right, you have a large vessel that's used as your design vessel. That's the largest vessel that typically comes at your terminal. But what if most vessels that come in are much smaller than that? And also the impact of hazardous cargoes. And while Working Group 33 tells you that you should consider all these factors, it gives no more guidance on how you should deal with this. And so that's one of the things we have done in Working Group 211 is to try to figure out and give much more clear guidance on how to deal with these factors. A few other challenges faced by that comes from Working Group 33 is that abnormal berthing factor that, as it was stated there, only considered uncertainties in the berthing scenario and did not consider other uncertainties, for instance, in fender performance. And there was really just a deterministic approach to the fender properties where you subtract your manufacturer tolerance when you do your fender design. So Working Group 33, or Working Group 211, we took the approach of doing a statistical and reliability-based approach to how to select the abnormal berthing factor, or now the energy factor. So we started by developing safety classes similar to those that are used in the Eurocode or ASCE 7 here in the United States. We want to use a rational approach similar to load and resistance factor design, but we're using energy instead of force in our calculations. We wanted to include uncertainties in fender performance, develop specific guidance for the contributing factors, and ensure consistent targeted levels of safety. So the curves you see here, the left curve you can imagine is the load curve, the energy, the distribution of berthing energies for vessels coming in, and the orange curve is the distribution of fender capacities. And this little highlighted area down between these curves is typically thought of, well, here's your failure region for fenders or any other structural system that can be represented by this. So we started by developing safety classes for berthing. From A to E, there's a lot more text surrounding these safety classes here, but it basically ranges from negligible or low consequences for loss of human life and economic damage to very high consequences for loss of human life or economic damage. And if any of you are familiar with ASCE 7, it's mostly focused on loss of human life there, but on a berth, it's just as important to consider economic damage as well. What happens if you lose a fender? Do you have to stop operations? Can you keep going? Is it going to be quick to replace the fender? How much downtime do you see if your fender actually fails? So based on these classes and based on various probabilities of failure that are published both in Eurocode and in ASCE 7, we developed these specific suggested probabilities of failure, which might not tell you much at the face of it right now. But again, if you compare to ASCE 7, we'll see that for Class A, which is the lowest consequences of fender failure, actual probability of failure 1.08 times 10 to the minus 4 is very close to or highest probability of failure. The highest probability of failure is very close to the highest probability of failure published by ASCE 7. The same thing goes for our most or highest or lowest acceptable probability of failure of 1.0 times 10 to the minus 7 as published by ASCE 7. We have 9.96 times 10 to the minus 8. as we have targeted here in this work group. So targeted probabilities of failures and safety levels are very similar to what is used in the United States right now. So I've talked about failure of Fender system, and an important thing to think about is what constitutes actual Fender failure. So our selected failure point for the fenders is the rated deflection of fenders. I think we all know that most fenders don't actually fail at this point. So, but the important thing to remember that the fender is not a standalone structural system. It actually interacts with the wharf or the structure that supports it. So, and shortly after you reach that rated deflection, most fenders will stop acting as the normal energy absorption unit. The behavior changes, and you will see a rapid increase in reaction force. And that's something that can jeopardize your supporting structures. So it was decided as part of the working group that the rated reaction force is a good selection as a definition of failure. It is, the fender doesn't necessarily fail, but at that point you start jeopardizing the supporting structure. One more important distinction is that probability of failure of a structure is not a probability of exceedance of load. Those are two very different things. So the highest acceptable annual probability of failure that we have is 1.08 times 10 to the minus 4, so about 0.01%. Annual probability of exceeding a 50-year load is about 2%. And so those are two very different things. So it's important to remember that if you exceed your load, doesn't necessarily mean that your fender system will fail. So a few things that we actually looked at as part of this work was, well, for instance, what's the effect for vessel size? And now we have actually very clear guidelines in place for that. We have three classes: low variation in vessel size, moderate variation in vessel size, high variation in vessel size. Specific numbers for your coefficient of variation of the size of the vessels coming in. So from these numbers here, you can actually, if you have data on the vessels coming in, you can go right into this table. You can say, do you have low, moderate, or high variation of vessel sizes? Then you can go to the next table. Here's berthing energy factors, or abnormal berthing factors, as we thought about them before. And how do these values now vary based on berthing condition, monitored, favorable, moderate, or unfavorable, variation in vessel size, and then what reliability class you're in. And I wanted to point out that in most cases, we think that the reliability class most berths will be in is class A or class B. I mentioned earlier the really high berthing velocities that were observed Port of Bremerhaven for the very large container vessels, and we wondered, why do those fenders not fail? And really the key answer to that is that you're not just contacting one fender coming in, you're contacting several fenders. So we did a study to try to figure out how does multiple fender contact actually affect the results. So you have more closely spaced fenders, you can actually get energy absorbed by many fenders coming in, depending a little bit on what berthing angle is the vessel coming in at, and how far the fenders spaced apart. If you're coming in at the parallel berthing, you can contact a lot of fenders. So really what you're looking at here is what's your distribution of berthing angles, what's your fender spacing, and how does all this affect your results? In general, berthing angles for container vessels are much lower than the design values that are currently in use. Typically, actually, they're lower than 1 degree. And I think the general value that's published in Work Group 33 is you should use a berthing angle of 6 degrees in your fender design. You can see here below there's here's the distribution of berthing angles, and you see the vast majority of these in Rotterdam are below 1 degree. Go to Bremerhaven, it's a little bit different, but still typically low berthing angles. After going through a lot of work on this, we now developed energy factors where you have the chance of multiple fender contact. And again, same table as before, just lower values because you have a good chance of contacting more than one fender coming in. I mentioned berthing frequencies, how often do your vessels come in? So our reference point is 100 berthings per year, as you see to the right. Really, if you have vessels coming in, say 10 times per year instead, we'll see much less impacts on your fender, much fewer impacts on your fender, and you have a lower chance of exceeding the rated energy capacity of these fenders. So 10 berthings per year, you can probably look at something like 85% you can reduce your required berthing energy by about 85%. One berthing per year, you're down close to 70%. So we have developed adjustment factors based on this. Similar if you go the other way around, maybe for a ferry terminal, if you're at 1,000 berthings per year instead of 100 berthings per year, well, now maybe you have to increase your required energy by something between 1.15 and 1.2. So again, clear guidelines on how to do this, and numbers presented as long as you have the data for vessels coming in. So at the end, I just want to mention really quickly about my personal experience working or being part of a PIANC working group. We cover really interesting technical topics as part of the working group. It's great opportunities for young professionals to be a part of this. You really get to collaborate with the best experts around the world. And that's kind of a nice thing about PIANC committees. They're international committees. You get increased depth of knowledge. You get new contacts from different countries. You might get input for new research that you can do yourself. You can develop your own personal brand as part of this working group. There's meetings in different countries, so maybe you get a chance to travel some. If you can go to these the meetings. We did some online meetings as part of our working group. I think it's possible if you know the people in your group, but it will be a slightly longer process if you go that way. And it can be, as I have experienced, a little bit difficult for people outside of Europe, since it's really difficult to find good times to meet when all your members are spread all across the world. Want to mention at the end, we do have a LinkedIn page. Please visit that. We post updates there on a regular basis on how the work is going with our working group. You can find that there. And that's it. Thank you very, very much for your attention. I think I'm going to stop sharing my screen, see if there are any questions for us here.
Okay. Thanks so much, Rune, for that very informative presentation. And we have had a few questions come in the chat panel, so we'll go ahead and dive right in. Our first question is, very little information is available for smaller vessels, and especially if they do not have tugboat assistance. The Working Group 33 recommendations highly overestimate the berthing velocities, resulting in out of proportion fenders for small ships. Any new insight on this?
So, depending what we mean with small vessels, we are mainly looking at larger vessels here. I think maybe it is above about 30,000 deadweight tons. I think in many cases for smaller vessels, the fenders don't necessarily even function as an energy absorption unit. Maybe they're just more there for protection. Many smaller vessels will carry their own little fender system. It could be tractor tires, something like that that's hung over the edge of the vessels. But it is a difficult topic, and there isn't really that much good data available on the really small vessels coming in.
Yeah, and for more information on that, we got a response to the size, less than 10,000 DWT inland rivers.
Okay, Yeah, so I can mention, and it hasn't been an official part of this working group, but we are in the process of developing design standards for piers and wharves under ASCE here in the United States. We actually do have some data for barges under 10,000 deadweight tons. So there is some data available. It's just not part of this specific document.
And for the interested parties, is there a place they could go to find that information? Is there one repository that they could look for?
There has been some presentations given on this already at a couple of conferences. There hasn't been any official published data for these as part of a design document, but we think that these velocities for smaller barges can make it into that the design standards that I mentioned.
Okay. Thanks for that response. And I'll take a pause right now to remind folks, if you do have a question to ask, drop it into the chat panel to everyone or to meetings, and we'll go ahead and address it here. The second question we've received so far is the safety factor developed for classes A to D seems very large, mostly if one considers that structural engineers will consider additional safety factors in the calculation.
Okay,
yes.
So, yes. No, yeah, I understand I think I understand the question there. And it is important, and this will be part of the ASCE standards again. Now I'm relating this directly to what's happening in the United States. And any load factors applied to berthing forces, it's important that you know what reaction force from an offender should you apply that load factor to. And there's going to be clarifications coming on that in the future on how to actually do this. Right now, the guidelines aren't very clear on that, but that's actually something that's being worked on now. So to try to avoid that you are over designing the supporting structure.
Okay. And we have another question here that looks like a callback to the first question.
Okay.
How about the speed without the tug?
Yes, I think we will have guidelines for how to deal with that, to deal with the cases where you don't have tugs. The velocities that are published now, they're all tug assisted. But I think we will have some adjustments of the velocities based on non-tug assistance. But without the tug, you will have a vessel that's much more difficult to control, and you will expect to see higher berthing velocity.
Okay. Thanks for that. We'll move right along. What is the estimated economic impact for a design performed in accordance with the 2002 guidelines compared with the new guidelines?
I don't have a straight answer on that, and I know there are discussions happening right now on how do the results for Fender design from our document compare to a Fender design in accordance with Working Group 33. It's to be seen, and I will point out that what I presented here, although we're very far along and everything, there are important discussions that we need to make or need to have to make sure that we're not creating changes that are too large, especially if things aren't perceived to be unsafe right now. But there will be discussions on that topic. And I can mention too, at the PIANC America conference in Fort Lauderdale, there actually is a paper that will be presented by Working Group 211 there that will do exactly that, compare designs from this working group with designs using the guidelines from Working Group 33.
Okay, that's great to hear. Our next question is, in regards to hull pressures, are there also guidelines relating to ship's hull form, like belting, included or updated?
Yes. Yes, there will be. There will be guidelines on how to deal with belting, and it really changes the load on the fender panel. Instead of getting a surface load, you will get, you might get a line load on the panel and really develop high moments in the panels, but there are guidelines for how to deal with that.
Okay. And in regards to Fender system design, are there also aspects relating to the panel design, like load cases, to consider? Same for chains, weight, shear chains, etc., handled in the report?
Yes, the short answer is yes, there is.
Okay, that's great. And our next one, has data been collected on past failures for fenders designed in accordance with the past guidelines?
Not that I know about, and you'll probably look, the problem is, right, if you have a fender that's failing, if you want real data on what actually happened, you need to have a berthing velocity system in place, which tend to control berthing velocities better. So I don't think there's a huge number of data points available there. And it's also important to remember that or at least what we talk about as a failure point, you might not see that you have reached that point on the fender itself. You might not show actual damage in the structure. You might have just overloaded your structure a bit, but you might not see anything if you're thinking that point of failure. Where the fender actually ripped apart, yes, there are some cases out there, but it is difficult to get data for that.
Okay. And our last question here before we move on to close out today's webinar is there are a lot of folks interested in this topic, but obviously the report will not be out this year. You said hopefully sometime in 2023. So yep. When that report is released, where could folks go to find it?
Then they can download that report from the PIANC website. And I think it's a good recommendation to people if they want to download any PIANC reports to be a PIANC member, because I think it pays for itself for the first report that you download, basically. So if you're not a member, you have to pay for it. If you are a member, I think these reports are free to download.
Okay. Thanks so much, Rune. And with that, we're going to go ahead and close out the rest of the webinar.
Before we finish? Yes, I just wanted to really give credit to all the members in our working group who's worked on this document up until now, and to our chairman who's really set the good standard for how to run a professional committee, and also to Alfred Rablos who's been in charge of a lot of the research work that's happened here and also developed a lot of the slides in this presentation. So I just wanted to make sure they all got credit too.
Very kind. It is a team effort, isn't it?
Absolutely.
Okay. Well, we'll go ahead and close things out. I want to thank everyone again for joining today's webinar. And I just want to say I hope you'll join us at future PIANC USA events, such as the PIANC America 2023 conference taking place in Florida in April. Like Mr. Iversen mentioned, a special session on PIANC's updated Fender design guidelines will be featured at the conference and will offer more detail than we were able to cover today. So we do hope to see you there. Finally, we'll be sharing 2 links to close out today's event. First, all participants will be eligible to earn 1 PDH for their attendance. You can follow the link in the chat panel and use the password Fender to get your customized PDH certificate. That password is case sensitive and it is all lowercase. Second, we greatly value your feedback. You'll also find a link to a brief 5-question evaluation form in the chat panel. And if you have a minute, we would really appreciate your input on today's event. And that does it. I want to say thank you again for joining us today to learn about PIANC's updated guidelines for the design of marine fender systems. I hope you have a great rest of your day.
Thank you very much, everybody.